No. LaTeX not required for this course.
Okay.
It's pretty good.
Yeah.
So what did they go up to? What part?
For what?
Dune.
So this is Dune 1. They go up until he kills a man.
Right there.
Yeah, at the siege? You mean?
Before the siege even. When he kills Jay something, I forgot his name.
Wait, this is the second book series?
What?
Or something?
Yeah, Dune. He
Paul kills who?
The first guy he kills, literally.
It's at the siege, isn't it?
It's,
Because he doesn't get to kill any Harkonnens until he gets to the
yeah,
siege,
no.
and then it's a ritualistic battle.
Yeah, it's that.
Oh, yeah, that's at the siege, right?
Not in the movie. In the books, I think it is. In the movie, he challenges him on the spot, and they don't go to the siege first.
Boo!
There are very few changes, and that is one of them. They had to cut a lot.
Because he's forced to adopt his family after that.
Yeah.
Doing Eternal.
They're all walking to the siege, and they're dragging his body behind them, which is Loki.
All right. Sorry. Looks like I went ahead and transitioned already here. So anyway, to continue with what we were doing last time, of course, go out and watch Dune. If anybody's watching this, nobody's watching this. But anyway, we were starting. We went through a couple of examples of breadth first search, right? Or not a couple of examples, but this one main example where the idea with breadth first search is if you start at a particular vertex here, you branch out to the vertices that are immediately adjacent to it first. A, C, D, and G are in B's neighborhood here. And then only after you've visited things that are distance one away, and distance here being number of edges because it's an unweighted graph, then you start going to things that are distance two away, right? Here, and what else? E and F, right? So the idea of breadth first search is that you search the closest initial vertices first before going deeper into the graph. And here again, closest means distance, which is simply just the number of weight edges. It's not with respect to any edge weights, okay? So what I want to do next is, let's go ahead and codify this using actually write pseudocode here. So first of all, I'm going to start with the main function here, the main entry point, you should say, of breadth first search. Similar to what we did with depth first search, because if you've got a graph that is disconnected, it has multiple connected components over here, right? And you start BFS or DFS, it doesn't matter, on one of these components, you'll never end up visiting this other component unless you start over at one of those vertices, all right? So what we need is a main kind of function here to get us started so that we make sure that we're not missing any of those vertices. So BFS, I'll call it main here. And it takes a graph G, right? And again, the input here is a graph G equals V comma E. Right? It could be directed, it could be undirected, it doesn't matter, this will work the same. The only difference is looking at the neighborhood. Only outgoing edges define the neighborhood. Incoming edges, you don't get to go against the grain, so that's not your part of your neighborhood. All right? All we're going to do is set up the actual BFS algorithm here for each V in V, color V white. That is unvisited. And again, from a practical perspective, that just simply means having some sort of flag value in your program that says that this is an unvisited vertex. It could be an integer. It could be visited, unvisited, process. It could be an enumerated type. It could be one of a million different things that you could do to keep that idea. All right. I'm going to initialize a counter to 1. Right? Or actually, sorry. Let's go with 0. There we go. And note here that when we did the counting, right, 1, 2, and then 4, 10, 3, 7, right? These were discovery times and finishing times. Do we really need to keep track of both of them? Remember that it was a queue that everything went into and then came out of, and that was the order. So discovery time is going to be the same thing as finishing time, at least or the overall ordering. The difference in these numbers is only telling you how many vertices were visited between discovering this and then finishing it. Right? And that doesn't give you all that much information. So it might not be that useful. But we'll go ahead and nevertheless keep track of it maybe. All right, so for each V in V, right, if V is white, right, that it means unvisited, then we'll go ahead and visit it with this BFS algorithm, G starting at V. So you can see that if we explore the entire graph on the first iteration of this algorithm, then everything will end up being colored gray or black, black because it's finished. And so we will end up only going through one iteration.
You could keep a track of the number of times you've run that specific BFS algorithm.
In fact, that for loop, right? You explore the entire graph and you end up, every vertex is black after that, and you don't have a second run of this for loop here, then you know that it's connected. If you even have one run after one BFS and there's still a white vertex in there to be visited, you know that it is a disconnected graph for undirected graphs, of course, right? So already we're seeing applications of these basic traversal algorithms. That's the main. Let's go ahead and now define this subroutine right here. Okay. This is the actual BFS, where we're taking a graph G and an initial vertex V. So again, the input here is a graph, G equals V comma E, and a start vertex, V, in the vertex set. Sometimes little v's and big v's start to meld together. So if you want to, you can go ahead and switch over to X and Y, right? I'll just go ahead and keep it like it is here. Because with its typeset in LaTeX, you know, then it's obvious that there's a difference, okay? The first thing that I'm going to do is I'm going to increment my counter, because remember I started it at I started it at 0, and so I'll initialize that before I start the entire process, okay? Q is going to be my empty Q. That's my data structure that I'm going to use. I'm going to put vertices in it as I discover them, and then I take them out and process them in that order. Right? And what I'm going to do, the first thing is I'm going to NQ, so Q dot NQ, that initial starting vertex, V. I will also color V gray, because it is visited but not processed yet. And I will stamp V with count. This is the discovery time. Okay? Okay, now that I've set up my queue, again, this here is just the initialization. Now I need to go into a loop here. Right? Now let's think about this. I've got this queue sitting here, and I've got things sitting in the queue. I don't know, X, Y, and Z, dot, 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 right? What's the next thing that I process? I pull out whatever's over here. And I process it. And by processing it, I mean whatever you're going to do with the data that's stored in there. You color it black. You timestamp it with a finishing timestamp if you really want to, and then you move on, right? But what else do we do? When I've got X here, I need to look at its neighborhood of X. Right? And if I've got, there we go. If I've got gray vertices, that means that they're already in the queue waiting to be processed. I don't go to gray vertices. If I've got black vertices here, of course I don't want to process them twice, so I ignore those. So what am I going to do with every white vertex in its neighborhood? I'm going to NQ them in some order to set myself up for the next time I do this. Now, when do I stop this entire process? when there's nothing in the queue. Right? Just like the last algorithm, once the stack was empty, we were done. Right? So while the queue is not empty, right, I will do the following. I will go ahead and dequeue it, and here I'm not even going to bother with peeking, because once you dequeue it, you are definitely going to process it, and then you're done with it. So queue dot dequeue. By the way, is that how you spell dequeue? No, that's what word is that? That's that's a deck, right? And what is a deck? A double-ended queue, something where you can push and pop on both ends, because a deck can be used as an implementation for either a stack or a queue. So dequeue would be like this. Right? And Dairy Queen has misspelled their name for many, many years. All right, nobody goes to Dairy Queen. Right? Fine. We could go for a blizzard. All right, so for each vertex y in the neighborhood of x, right? For each, actually I should move this over. Let me go ahead and just put this in here. Oops, too far. There we go. For each white vertex in the neighborhood, I will go ahead and increment my counter. I will color x gray, or it's not x, sorry. I will color y gray, stamp y with the counter, and then enqueue it. That's it. Otherwise, no. You could, of course, process. You could process x here, right here, once you dequeue it. Or what I've chosen to do is to process it after I've processed its neighborhood. And so I'll go ahead and put that down here now. I will increment my counter, ++, because it's going to be finishing time of the of x, and I will process x, whatever that means, and then I will color x black and stamp x with count, and this is its finish time. And that's all within the while loop right there. Right. Any questions on that? Yeah.
So there's no backtracking in rough first search,
Nope. No backtracking. There's no breadcrumbs like there would be with a queue, because a queue, this is where you came from. The stack is, this is where you came from. In this case, the queue is not where you came from, but a visualization of, and I'll go ahead and use blue here, that if you were to take this BFS tree and read it top to bottom, left to right, that's the order that they got into the queue, right? And again, this criteria right here, for each white vertice in the neighborhood, this could be lexicographic. It could be with respect to weight, like the edge weights or whatever, connecting those two x and y together, etc. It could be random order. It could be, doesn't matter what order, right? I'm just exploring the graph. But in any case, if you do have an order like you do in your homework, you will need to respect that order at this point in the algorithm. Okay. Sorting the labels or maintaining a sort, or generally what you do is you can provide a lambda function, assuming that you're using Python here, you can provide a lambda function that says, I want you to give me a stream. Is it called streams in Python? Iterable, there we go. Iterable in with respect to this comparator or whatever it is, right? Or again, you can dump it to a list, sort the list, and then go through the list. Right? That's probably the most straightforward way of doing it. But the Pythonic way would be some sort of a lambda function.
What was that?
A lambda function is basically an anonymous function. Help me out with the syntax, everyone.
Lambda.
Is it literally the word lambda?
Yeah.
And then like x.
Colon.
Oh, is it colon, not arrow?
Okay.
Colon, I don't know, square root of x. Math dot square root of x. And then what you could do is you could do in a list comprehension here. Actually, no, you wouldn't want
I don't know how you would use list comprehension.
yeah, you would just, well, if you're going to use a list comprehension, then you would just say, you wouldn't even use a lambda, you would just use a square root of x such that x, or so 4, no, it's not even colon. What am I thinking? 4x in whatever list you have, right? That's a valid list comprehension, right? Right. And that converts a list of like 1, 2, 3, 4. It would give you a list containing the square roots of 1, 2, and 3, and 4. Right. But that's Python, not a Python course, not a functional programming course. Right. All right, questions on BFS. All right, then let's make some observations. First of all, if you have a BFS tree for undirected graphs, again, there are no possible back edges or forward edges. Because if you had such an edge in that BFS tree, let's go all the way back over here. Sorry. If you had this forward edge right here that we talked about last time, you would have visited that because H would have been part of B's neighborhood. So there's no such thing in an undirected graph of a forward or a back edge. In a directed graph, you can, of course. In a directed graph, back edges are possible, but forward edges are not. And again, forward edges going down in that BFS tree are not possible because you would have explored that with respect to this guy's neighborhood up here. But a back edge is perfectly reasonable and possible because that's not in the neighborhood, right? Again, this one over here, if it were oriented this way, that's not possible because we would have explored that edge. But if it were oriented this way, then that is possible. That's called a back edge because it's H or B is in H's neighborhood, but not necessarily the other way around. And in both undirected and directed graphs, you have potential cross edges. Both have potential cross edges, right? Edges that do not, that connect vertices in the BFS tree that are not ancestors or descendants. Right? Descendants. There we go. And what that means is like cousins, siblings, if you look at it with respect to a family tree, cousins, siblings, second cousins, once removed, etc. Right? BFS may need to be restarted if it is a disconnected graph. Right? Or if it is a directed graph such that some vertices are reachable but others are not. Right? And what I mean by that is let's consider a graph here. Right? Let's consider a very simple graph on 1, 2, 3, 4, 5 vertices. This is kind of the graph that I've been drawing throughout this thing. Right? But now let's think about it in terms of a directed graph. Let's go ahead and direct it that way, direct it that way, that way, that way, that way, that way, and actually no. That way and that way. A, B, C, D, and E. All right, so from A, can I get to any other vertex in this directed graph? Nope. So A is a sink. Right? Why do we call them sinks? What does a sink do? In the middle of a sink, maybe we should call them drains instead, right? Yeah, it doesn't come back up. You don't want it to come back up, or then you're getting sewer back into your house, right? You don't want it's a sink. It only goes down, right? It only goes down into that vertex and then down into the drain and gone. What about E? Can I reach E from any other vertex? Can I get to E somehow as a destination? Nope. E is a source. All right. So, two new terminologies here. But other questions like, can I? If I start at E though, could I get to A? Yeah. Go to B, then go over to A, or go to D, then C, then A. Right. In other words, there are multiple paths here. Okay. One of them is shorter than the other. Right. What is the shortest path going from E to A? Probably this one. Right? Where you only have 1, 2 edges to traverse. This one, 1, 2, 3, 4 edges. Right? That's probably the longest one. 1, 2, 3. So efficiency. Do you want the shortest path from any two vertices? Do you want the longest path between any two vertices? Those are things that basic questions that we need more graph algorithms for. Right? And we'll talk about that here in 1 second. But otherwise, it may need to be restarted because if you start your BFS at A, can you go anywhere? Nope, you're done, right? So you need to restart it at, say, B. Once you're at B, then you can explore to A and then D, and then from D, you can go over and explore C. So if you started it at A, it would look something like this, A, and then you can't go anywhere. Then if you started over at B, then you could go to C and D. And then would you be done exploring the graph? Have I explored all 5 vertices? Nope. E. Right? And then of course you would see that these are going to end up being E goes to B and D. Oh, wait. I've got 2 C's, sorry. C, then all right, from B, I can go to A. Okay, so I screwed up on my BFS. Sorry. From B, where would I go? Only to D. And then from D, I could go to C only. There we go. Now it looks like that. All right, so these green things are cross edges, right? Because they connect between 2 disconnected directed components. There is no way that I can go from A to any other component in this graph. From the perspective of oriented edges, it is isolated because it is a sink. Right? What other 1, 2, 3, 4, 5, 6, 7, and I've got 1, 2, 3, 4. What other vertices are here? Or whatever other edges, sorry, excuse me. C to B. I'll draw that one in red. Why? It's a back edge. Forming what? A cycle. Okay? So a back edge implies a cycle. A cross edge might imply a cycle. You have to be careful. Right? That's way more complicated to reason about. What other types of edges do we have here? I think I'm down to just 2. What am I missing? E to D. There we go. And then what's the other one? I need something going into A, so here, C to A. And that is not a back edge because it's not in the same connected BFS tree. All right, so these are, again, cross edges, and this is a back edge. All right, cool. So cross edges in a BFS tree can connect cousins, aunts, but never descendants or ancestors, etc. All right. What about an analysis? What do you think? Exact same as before, right? You might consider as your elementary operations potentials for processing a vertex, right? Likely the most expensive, right? You might consider traversing an edge, right? And so therefore it's going to be 2m, right? Which is order m, if that's the case. Well, for processing vertices, you only process them at most once, right? So this is going to be n, which is order n. You could say examining a vertex to see if it is black, gray, white, in order to determine that you need to go to it. And that is, of course, going to be also 2m, because you're looking at a vertex, right? You examine it once from one perspective, you examine its neighbor from the other perspective, so like kind of like a handshake lemma, right? You end up doing it twice for each vertex, and you end up doing it like this. You do it twice for each edge in the graph. So you might examine a vertex more than once, but you're only doing it at most twice for each edge. That bounds it above by m. All right? So, or overall, if you want to capture all work, it would be order n plus m. Right? And that's just the hackish way of thinking about it, I think. All right. So questions on that so far? No? You certainly have everything that you need for next Friday, by the way. I think you have to do DFS, BFS, and is that it? Or maybe connectivity or something like that as well. I'm not sure. Yeah, go ahead.
What, I don't know, I don't remember like discussing like what like types of things we could do for processing a vertex. Like what would be some examples of like.
Well, the examples in your actual programming assignment are simply just print them out. Print them out to the standard output, or put them into a list and then print the list out. But again, ostensibly, why do you look at graph theory? Maybe we didn't motivate this properly. Why are graphs used? Between what? Find paths between what? Cities. So geography, right? And cities are points or points of interest, and you have connectivity between them, either as the bird flies or as roads go, right? And you've got a cost associated with that. That's a weighted graph. You've either got distance or miles per gallon, or you're charging for trucking fees. It's 50 cents per mile or something like that, etc. What else is a graph?
Facebook friends.
Say what?
Facebook friends.
Facebook friends, social media, social networking, right? That's a network, right? Networks are also, actual wireless networks, right? In range, sending something over several hops in a network. Is it more efficient to send it to that relay station or that relay station because it gets there quicker, right? There's a latency involved. There's throughput involved, right? And each one of those is some sort of metadata on those edges. And stopping at that location or being processed at that node or whatever, there's some cost associated with it. What else? Think of something not computer science. All right, chemistry. Tell me what water looks like. H. H. Oh. What kind of bonds does anybody have chemistry background? Please. And what? Well, yeah, but are they covalent bonds or I don't know? Is it like this? Oh, sorry. Is it something like this?
No, it's double bond. No, single bond for me.
Is it single bonds?
I think so.
Yeah, it's got to be single bonds compared to double bonds.
All right, there you go. Is that H2O?
Yeah.
All right, there you go. That's water. Right? What is that? It's a graph. Right? So think back to computer science 2, where you created databases, and you created an ER diagram. What is that? A chore, yeah. But with the picture that you ultimately generated, it's a graph. Right? UML diagrams, right? This inheritance hierarchies. At the end of the day, guess what? Everything's a graph because everything's a relation. Think back to 235. What is a relation? A relation is a subset of the Cartesian product of two finite or infinite sets. Right?
Sure.
Remember that a relation is a subset of all A, B, such that A and B are in some set. What does that look like to you? A and B are related to each other. If it's an ordered pair, then it looks like this. If it's an unordered pair, then it looks like this. What is it? It's a graph. And everything is a relation. Because if you want to talk about, if you want to get as abstract as you can, you're talking about entities and the relationships between those entities. And guess what that is? A graph. Right? So everything is a graph. Right? Or everything can be modeled as a graph. Show me one thing that can't. Because I'd really like to know what it is, so I could have a counterexample to that statement.
Well, even if you could say it could be graph in relation to what it's not related to.
Well, yeah, you could have different types of edges for a positive relation or a negative relation, or just make those weights +1, -1, right? Markov chains, et cetera, et cetera. Right? All right, so let's start thinking of other applications that we could potentially solve with just these two simple algorithms. The first one is connectivity. In fact, I'm going to put this as a subheading, connectivity. Right? Given a graph and, say, two vertices, x and y in V. Does that render? Good. Right? So given a graph, and it doesn't matter if it's directed or undirected, G equals V comma E, and say two vertices that are in the vertex set, determine if x and y are connected. Right? So what do I mean by connected? I don't just mean that they have an edge, right? I mean that does there exist a directed, undirected, or directed path from x to y? Very, very basic question, right? Usually, sometimes if it's directed, we'll use the following, and I have no idea if my LaTeX here will support this. There's a path going from x, right squig arrow to y. Okay, did I spell it right? Right squig arrow. Okay, it's not going to render it like that. That's probably an AMS package. Nope, that's not going to render either. Fine. I'm getting greedy here. There we go. I got it. I had to go into full math mode here. Right? There's a path going from x somehow all over the place over to y. Right? That's for directed graphs. Right? If you want to know the LaTeX for that, of course, it'll be available in the Markdown when I post this to GitHub. Right? And there are lots of ways that you can ask this question. Right? So let me go over here and visualize it. So here's my graph. Here's G. And here's a vertex x in it. And here's a vertex y. Suppose that there is some path in here that goes from x to y. There's some sort of intermediate vertices in here. Right? Okay? So answering the question of does there exist a path or not, what are the answers that you would give me? For example, let's just go with a more concrete example here. I asked you before, does there exist a path from E to A? Yes. Does there exist a path from A to E? No. In other words, you gave me a yes or no answer, right? That problems that have that are posed such that there is a yes or no answer, or alternatively, what else can we use for yes or no? If we were actually programming this, true, false, right, etc. 0, 1, or 1, 0 in this case, right, etc. Right, are decision versions. Right? You're making a decision, a yes or no decision. Here's a graph. Here's x, here's y. Does there exist a path from X to Y? You simply have to answer yes or no. Now, does the answer of yes or no tell me what the path is? No. Right? That would be called a functional version. Right? So, problems that require the output of an actual solution are functional versions. Right? That it maps your input to an output that is a witness or certificate to the yes/no question. Right? So in this case, I'm not simply just asking is there a path or not. Right? I'm asking, given g, x, and y, if there is a path from x to y, output it. If not, output some flag value. Right? Nil, none, phi, whatever. Right? That tells me that there is no path, and if there's no path, then I can't output it. Right? Empty list, empty set, whatever. Right? That's a functional version. Now let's think about these two versions. Okay? What if I just simply answered yes or no? Does that help me in finding the path? Nope. I don't know what is the path. But if I said, yes, there is a path going from X to A, then over to C, then over to D, and then over to Y, right? Do I know the answer to both questions? Both versions? Yeah, right? Because if I have a path and I can verify that path, then I can answer yes, that there is definitely a path. This is a witness. This is a certificate that's of authenticity, basically, that says, yes, there is a path. Here it is, right? And you can verify it. You can look at this graph and say, oh, yep, that is a valid path. You weren't lying, right? That's a certificate or a witness to that fact. Can I use a yes or no as a certificate? I just have to take your word for it, right? You say, yes, there is a path. Okay, what is it, right? And then you're sitting there silent, right? There's a concept known as oracles that we'll talk about later. So those of you, you are familiar with chemistry, so I'll call on anybody else that is familiar with Greek mythology. All right? So what is an oracle in Greek mythology?
Someone who can tell the future, has messages from the gods.
Exactly. It can tell the future and has messages from the gods. Now, the reality is that the oracle was actually just somebody who sat in this cave that was full of methane, and they got high and started hallucinating, and that was their prognostication, right? So that's the reality. But let's look at the myth, right? The actual myth where the oracle, you went to the oracle and said, "Will I be rich?" And the oracle just said yes or no, right? Did the oracle tell you how? Nope. Through this convoluted, yes, you will become rich because you will have the most terrible life in the world, in all of history, but on the last day, you'll win the lottery. Is that a satisfying answer? I mean, they said yes, right? So in Greek mythology, it was always the oracle telling you the wrong thing. The truth, yes, that's going to happen, or no, that's not going to happen, but none of the details. And that's what led to Greek tragedies, right? So the tragedy here is that if we have an oracle for a yes or no question, that doesn't get us anywhere closer to the actual answer. We need a functional version of it. Or we need to be able to game the system and use this yes or no answer in order to build this path. For example, what if I said, here's X, and here's its neighborhood, A, B, and C. And then here's Y over here, with incoming edges. Now what if I changed my question to the oracle? And the oracle initially said, yes, you can go from X over to Y. Right? They said yes. Okay. That doesn't help me build the path, though. But what if I change my question? What if I change the question to, does there exist a path from A to Y? And the answer is no. Does that tell me where I need to go? Yeah, don't go to A. Right? Now, what if I ask the question again? What if is there a path from A, or not A, but B, to y? And the answer was still no. That eliminates that as a possibility. What if I asked the question, does there exist a path from C to Y? And they said yes. Take that path and now change your question again. Look at the neighborhood of C, right? How does that get me closer to the answer? I can start building my path. X goes to C, then goes to something, then goes to something, dot, dot, dot. You just keep asking this question over and over and over again. So, are these two versions really all that different? When you know the trick behind them, right? So now go back to your Greek tragedies and start asking better questions. Okay, will I become rich by this date, right? And the answer, no. Okay, will I become rich by this date? No, no. Then you can get lottery tickets too, right? You ask the oracle, will the number coming up this weekend include 5? No? Okay, cross that out. Will the number coming up this weekend include 6? No? Okay, cross that out, right? And as long as you know how the proper questions to ask, these two things can become equivalent. The decision version can be made into the functional version or vice versa. And then there's yet another type of question that you can ask. Right? Problems that require not only a solution, but an optimal, but the best solution are optimization versions. Right? I don't want to know that there's just a path from X to Y. Great, I don't care. There might be 50 paths, there might be 1,000,000 paths. What I want is the best path. That best path could be, for example, it could be the shortest path, or the longest path, or the shortest, or the least weighted path, or the most weighted path, right? Whatever your criteria is, right? These are usually called objective functions. What you are trying to optimize is an objective function. I'm trying to minimize the number of edges. I'm trying to minimize the total weight of the edges. In other words, I'm okay going 50 different edges as long as the sum total of all those weights is less than this 2-edge path over here, right? You could have something that looks like this in your graph. Going from A to B to C, 20, 80, but then there's a longer path, but they're all 1. 1, 2, 3, 4, 7. So which route do you take? Right? And this has real analogs to the real world, right? What if this is, yes, this is a shorter distance to go from city A to city C, but you're going by plane, and so it costs you $100. Whereas, yeah, you could go from a city A all the way over to city C here, as long as you're willing to take this long haul bus. And the bus only costs you $7, right?
Which is impressive with gas rates today.
Yeah, I have no idea which is more cheap nowadays. It used to be that the train was cheap, but might still be the cheapest route, but that's only if you're going to specific cities, because trains are kind of fixed. They can't just go anywhere, right? So those are 3 different types, and sometimes you can translate decision versions into optimization versions into decision, or vice versa, all throughout all 3 of these. In which case, we say that they're all equivalent, right? But let's go ahead and think of a few solutions here, potential solutions, right, to the connectivity problem itself. Given these 2 vertices, directed, undirected, it doesn't matter. Let's just answer the simple question. Does there exist a path from X to Y? What are some potential solutions for the decision version?
Yes or no.
Well, yes or no, that's what I want, but what about the actual solution? Well, an algorithm. I need an algorithm to do this. Right? Okay, run DFS. And what criteria should you be looking for?
Cycle.
Well,
Or no, sorry.
not a cycle. Yes, these connectivity questions can be rephrased as a cycle. For example, I could say x and y. Does there exist a path between them? Yes? Okay, great. Now, y to x. Does there exist a path between that in a directed graph? You could do a similar trick with respect to DFS and undirected graphs. You just need a little bit more information. In fact, let's think about that trick. X and y. I want to know, is there a cycle? In other words, are there two distinct paths? That's a completely different question. Because if you just run DFS on one and you get a yes answer, well, of course you're going to get a yes answer whether or not there's another path. So let's think of a trick. Again, looking at the neighborhood of x here and the neighborhood of y that we could exploit to find for DFS. DFS is answering yes, there is a path. No, there is not a path. A, B, C. What question do we need to ask? Suppose that the answer is yes. If you go to A, yes, going from A over to Y is a path. Now, how do I rephrase the question to determine if there is another path from X to Y that doesn't involve A? Get rid of it. Good. Right? Get rid of it. And now you've got yourself a new graph with one less edge. And ask the question again. If the answer is still yes, then you know that there is definitely a cycle there. Right? So you can use connectivity questions to answer cycle questions. And of course, vice versa. Go ahead.
How do I know if the answer is yes or no?
Well, that's
Sorry,
back to A here. How do you run DFS to answer the yes or no question?
If we traverse y, starting at x.
All right, start at X. And if you ever, here, run DFS, potential solutions for undirected. If you ever see Y, stop, answer yes. Right? Otherwise, if DFS has to restart to discover Y, the answer is no. Right? That's it. What are potential solutions for the directed case? What's an alternative solution, by the way, for the undirected case? How could I do it with BFS? Same criteria. Exact same criteria. Potential solutions for directed, though. So remember that you build this this DFS tree. That's way too far back now for me to jump all the way back, but there we go. Right. So in an undirected graph, there are only back edges and forward edges are the same. But if I had a back edge, that would imply a cycle, right? So how do I answer this question for just directed graphs? Again, start at X, and if you ever see Y on the main tree here, guess what? It's connected. Right? So potential solutions for the directed case is run DFS starting at X, right? If you ever encounter Y without starting over, then the answer is yes. Right? It's as simple as that. Now BFS is a different story. No, it's BFS is going to be the same. I keep mixing up cycles and directivity now because of that. But anyway, these are all you need. Just run DFS, run BFS, and instead of enumerating all the vertices, when you get to your sink, your destination, Y, stop. You found it. In fact, if you have DFS, you also have a solution, right? Because DFS keeps track of where you've been. If you start at X and you go here, you go here, you go here, what's in your stack? That's the path that you took to get to Y. Okay, take the stack, dump it to a list. It's probably already a list, and there's your path. You have a functional solution. Do you have an optimization solution? An optimal solution? Not necessarily. That's going to require more sophisticated algorithms. Dijkstra's algorithm or Floyd-Varshall's algorithm that we'll eventually get to. Okay? All right, it's a bye week, so, and you guys get a bye week too. There's no homework today, right? Okay. All right, so have a good weekend.